they will make more money out of just carbon credits than producing anything, because the Europeans or the Western world have done a lot of crime, so they have to pay for their guilt, and therefore the carbon credit becomes a bigger market for us. SAF is again a high value product. It really is, and the Honorable Minister, when he visited our stall today, I mentioned to him about SAF, and he said that this is multi opportunity hai. That was his words, and it definitely is, because we as a world consume 100 billion gallons of aviation fuel in the civil aviation sector. We are not getting into the defense side, and we are talking about at least 10% to be replaced by SAF in the next 10 years. So the opportunity is 10 billion gallons on a worldwide basis. So it is big. Other than SAF, syngas has its opportunity in itself, and again, India is the biggest in sugar. We are competing with Brazil, but in terms of the value-added things that we can do here, we can be the leaders. The sugar industry can pave the way for bringing this entire green hydrogen revolution across the country, because it's a significant chunk that you're talking. If you're talking about 17% of the 5 million metric tons or 6% of the civil aviation needs, this is going to be one of the most important sectors, and even politically that will bring a lot of power into the sugar industries. So I end up with, Kalam Sahab used to say this, and very relevant to the times that we live in, that unless India stands up to the world, no one will respect us. In the world, fear has no place, only strength respects strength. So unless we become a strength in energy, we will not be able to become that independent nation that we are really talking about. Thank you very much.
Thanks to BSI for giving us opportunity to share our work. Now I'm collaborating with BSI because I am responsible for both the organization. Now I am the Emeritus scientist in CMET also, so I am working along with as scientist and then the MIT-WPU MTech students and PhD students. So just I am collaborating some areas. BSI, we are collaborating with sensors, all kind of sensors we would like to have, like basically NPK sensors we are talking today. So we are working along with it. Then batteries, because we are working on hydrogen as well as we have a good facility of battery fabrication, lithium-ion battery, sodium-ion battery, lithium sulfur battery, and we are fabricating at a pouch level. We have demonstrated the two-wheeler battery and run the vehicle for 30 kilometers per mile. So, and all the materials have been indigenized in batteries. So one of the good material, like one of the anode material is carbon. Generally we use carbon, graphite as a cathode and anode. So we are collaborating with BSI whether we can make carbon out of their sugar waste. So that work is going on. Some of the good results we have achieved, but I don't want to. You say energy generation and energy storage. So both the applications we are working together. And we are in the quantum materials, quantum technologies now, because quantum materials are the future technologies, materials which is required for the quantum technology, as well as photonics. So all this we are collaborating with our MIT-WPU CMET for when its part is the materials and another part is the devices. So both quantum sensors, which also useful for agriculture applications. So considering this, today's my focus will be only on hydrogen for the photocatalytic process, the water splitting, as well as H2 splitting. Because we have now see all speakers already talk about biomass and other processes. So my today's talk is only on focus on photocatalytic process, which is using renewable energy source like sunlight. Apart from them, using our nanotechnology, how we can improve the hydrogen evolution in this case. So though we work on so many other processes like the thermal process as well as biomass degradation. All these we work like one of the process now we have hydrogen from e-waste. So that project is going on in Hyderabad. So we are producing some catalysts there in between in e-waste degradation where we get hydrogen, more hydrogen as compared to CO and CO. Most of the catalysts we use are, see, I will not go details about this hydrogen because we work for fuel cell and other things. These are the processes. We also work on steam reforming method because we have a nanostructure group. So we use different type of catalysts and see the performance. Then hydrogen from biomass also we are working along with VSA also, and for this biomass for the battery purpose. So there is in the electrolysis of water we have a project that using the solar light solar module we can give the energy to the electrolyzer and produce the hydrogen. This is a project required for Leh and Ladakh because there hydrogen and oxygen is very important there. So since oxygen level is low, so whether we can have such kind of models in the Leh and Ladakh. So that project is going on. So going to the coming to the point that hydrolysis of hydrogen by photocatalysis process, it's generally it is a photocatalytic process. It's rather different than the normal photocatalytic process. In this case, this electronic phenomena is very important because basically these are the semiconductors. In semiconductors, when there is a photoexcitation after under natural sunlight, they absorb the light and there is a photoexcitation. Then electrons and holes are generated, and then electrons and holes are responsible for this decomposition of water to produce hydrogen and oxygen. So what is required here is a good semiconductor catalyst which can absorb maximum sunlight. So its band gap within visible region so that it can absorb visible light and produce more charge carriers like electrons and holes, so that we can increase the efficiency of hydrogen production. So it is actually auto hydrogen and oxidation and hydrogen reduction process. So this is a very simple process. You can see here, it's a normal process. Simple at room temperature. We are taking water and with some at certain pH and our photocatalyst. This photocatalyst will absorb the sunlight and produce electrons and holes, and these electrons and holes are responsible for the hydrogen production. So this is a very actually this is a catalyst dependent reaction. So the key factor is how we can produce a very stable catalyst which can be utilized for many times. So there are sulfide semiconductors, oxide semiconductors, and nanostructuring of these materials also very important because that enhances the catalytic activity. Another source we are looking for the H2S because a lot of H2S is generated in refineries. Almost 8 to 10% H2S is generated in the refineries. Whether we can utilize this H2S, because now we are utilizing for the Claus process where sulfur is oxidized and we get liquid sulfur, and H2S is oxidized, we get H2 and sulfur, liquid sulfur, and liquid sulfur is used for fertilizer. But in our case, we can split the H2S into hydrogen and sulfur. This colloidal sulfur you get, this colloidal sulfur is a very active colloidal sulfur. We can use for as a fertilizer as well as in the pharmaceutical because they need a lot of sulfur. So this can be reactive sulfur is utilized for. So this is a mechanism where I will not go details on this because what is the requirement is now the criteria for ideal photocatalysis. It should be inexpensive, high chemical stability, absorption in visible region, because it's very, very important. If you want to run the catalyst in natural sunlight, then your band gap or your absorption of the catalyst should be in 400 to 800 degrees centigrade, 800 to nanometer, and stable towards the photoconductor. So these are the important factors for this photocatalyst. So our team is working on all these factors and producing the nanostructure catalyst. So we are more focusing on oxide photocatalysts because they are the stable catalyst and chemically stable as well as thermally stable. So modification of oxide semiconductors is very important. That we are doing it, and we are tuning the band gap between 2.2 electron volts to almost 2.8 electron volts. So that maximum means you can say the 400 to 800 nanometers range we are covering in these materials. So what are the modifications we are doing, like anion doping, then some transition metal doping also we are doing. Then some noble metals loading we do, because then we can have the fast electron transfer on the surface, so that there is a separation of electron holes will be faster and reaction will be much faster. Then nanostructuring of semiconductors is very, very important. When you nanostructure the semiconductor, the surface area increases, and then you get almost 20 to 30% more hydrogen evolution in this case. Then anion doping expand the photo response into visible region, because what is this doping is essential, because this doping will bring the this catalyst into the visible region for absorbing maximum sunlight. So these are the catalysts we generated, which we have fabricated in the synthesized in the lab, and I don't want to go details in it, because these kind of structures are also very, very important for the enhancing the hydrogen evolution. So here the cadmium molybdenum sulfide, because you see the structure, this honeycomb-like structure, that is really important to in the contact in the water and catalyst. So that's very important. So we get good hydrogen evolution, such kind of catalyst, because they have a good they have good stability, and we can repeatedly we can use this emulsion. Some of the catalysts we found they are not they are unstable, but initially their catalytic activity is more. So all these catalysts we also use quantum dots, and then different kind of structures, and evaluated that there are some kind of structures can give the very good photocatalytic activity. So this so from quantum dots to the semiconductor powders of 100 gram scale we are manufacturing in our lab, CMET lab, and utilizing for this purpose, as well as it is for hydrogen evolution, as well as it is for the battery fabrication, because most of these semiconductors we use as an anode in the battery, and we find that some of the like MOH2, because of these structures, the ion transport is much faster, so we use in battery fabrication. So another area we found that whether we can use quantum dots, because quantum dots is a very they have high surface area. So like semiconductors like cadmium sulfide, cadmium selenide semiconductors, these are very, very, very important, because they have the band gap within the visible region. But these are very unstable. These quantum dots are very unstable. We can keep it for 1 or 2 days, then the size is going on increasing. So we thought that a very typical example CDS and CDS-SE, these are the two quantum dots we have selected, and we found that they are unstable when we in the powder form or in the colloidal form. So we thought that whether we can have this in glasses. So we have embedded in the glasses, like it's a silicate glass. In the silicate glass, we have grown these cadmium sulfide, cadmium selenide, cadmium selenide, bismuth sulfide, bismuth telluride. All these quantum dots we have embedded in these glasses, and they are highly stable. And these quantum dots we use as a photocatalyst because they are highly stable up to 400 to 500 degrees centigrade. So we can make the glass powder and use this glass powder for as a photocatalytic purpose. So this is a simple as normal glass making process, and within this process you can have the only 0.5 to 1% of like cadmium sulfide and selenide in the silicate glasses, and then you heat treat this glass and grow. It's a very long process, maybe 24 hours, 30 hours process, where you can grow this cadmium sulfide. Right. So these are you can see here the cadmium sulfide grown in the glass, and you see initially it is only 300 nanometer absorption, but it has gone to in the visible region by when we grow the cadmium sulfide in the glass, like 2.48 electron, 3.12 electron volt to 2.48 electron volt. So this glass powder of yellow color glass powder we can use as a photocatalyst. They are highly dispersed in the glass. You can see if they see HRTM, you see that they are highly dispersed. It is only 2.5 nanometer, and they are highly crystalline. They are highly crystalline. You can see if you see the SCD pattern of this glass, they are highly crystalline, polycrystalline, as you can see. And in the same glass, if you can heat treat it at different temperatures, so in the same glass we can have the cadmium sulfide of 2 nanometer, 2.5 nanometer. The red color is 2.5 nanometer, and this is 5 nanometer ball. So same glass will have different color because of this size. That is part of the size quantization in the glasses. So these glasses generally used for optical cutoff filters for in photonic application, but this has been used as the first time for the energy generation from our laboratory. We have a US patent on this. So this is again a CDSAC quantum dots in the glass, different semiconductors, and where we can see that the absorption enhanced to 600 nanometer in the visible region, and very isolated quantum dot here. You can see highly crystalline. You can see this is in 60% SiO2 glass. It's a very typical glass composition we have to optimize because it's a very tricky thing. See, the density of the dopant and density of the glass should be different, because density of the glass should be much higher, much lower as compared to the dopants. So we have to define the glass composition, optimize the glass composition for particular dopant. So here is the CDSAC where we can enhance to 700 nanometer, and you can see all quantum dots. Basically, quantum dots means when you can fabricate or you can synthesize the nanoparticle of semiconductor close to their Bohr radius. Suppose cadmium sulfide has a Bohr radius is 3 nanometer, and if you synthesize the material of cadmium sulfide powder up to close to the 3 nanometer, then that's called as a quantum nanometer, like quantum dot of CDS, like say 2 nanometer to 5 nanometer, we can say that is a quantum dot. So with a very small glass particle of 1 micron, 2 micron, in that you can have the 2000 to 3000 quantum dots of CDS. That is the advantage of the nanostructuring of this material. So you can see all these quantum dots are on the surface of the glass. So that is utilized for the hydrogen evolution. So here you can see the initially glass is a transparent, and when we grow in the glass, then the absorption is enhanced to the visible region, and then we can utilize the proper glass for the hydrogen evolution. Then we use germinate glass because, as I told you, that the optimization of post glass is very, very important. So instead of SiO2, we thought that whether we can use germanium, because germanium is also very important in the semiconductor. And we use that, and when we develop serious quantum dots in the glass, this is first time observed that this, instead of hexagonal kind of series, we observe orthorhombic series. That is a very important, because orthorhombic series is very well known for the solar cell application, and this is the first time we observe in the glasses. So this is you can see that absorption from up to 800 nanometers here, and the growth in this glass is much higher as compared to silicate glass. You can see you can go up to 12 nanometer in this type of glass. Very scintillating color, yellow color, then brown color and black. Though you see that the black color, the transmittance from this glass is much higher, 70 to 80%, 80%. So this is the CDCC doped germanate glass. Again, we repeat it here, and you see here the quantum dots in the glasses, very nicely dispersed. And then we wanted to have bismuth sulfide in the glass, but we could not get bismuth in the glass, but we got bismuth particles in the glass. And here the advantage we got is that the band gap we can has been enhanced to almost to 1.7 to 1.8 electrons, which cover UV light to almost IR region, so that we get good spectrum of visible light. And we observe that this kind of glasses may give the very good photocatalytic activity. So this is the characterization. I will not go details. This is very. You can see the particle size. The particles are well dispersed in the glasses as well as on the surface. Is on 1.5 nanometer size. Okay. Then we thought that instead of sulfur, whether we can have the oxide type of materials. So Ag3PO4 is a well-known photocatalyst. Very this band gap is within visible region, 2.1 to almost 2.1 electron volt. But the problem of this Ag3PO4 is highly unstable. When we keep it open, then we get silver oxide and H3PO4 after decomposition at room temperature. So we thought that whether we can have in this glass, and we found that they are well dispersed in the glass. We grow and they are stable up to 200 degrees centigrade, or 300 degrees centigrade. So all these are glasses of Ag3PO4 doped glasses. They are not ionic glasses, they are quantum dot based glasses. Ionic glasses give the different kind of colors, but these glasses gives a very scintillating color, and these are used for in the photonic applications. So very small amount of Ag3PO4, maybe around 0.5 to 0.7%. So difficult to get analyze on XRD. So we have taken Raman, and Raman clearly shows there is a formation of Ag3PO4 inside the glass. See all these quantum dots of Ag3PO4 in the glass. See? And they are highly dispersed, and actually this Ag3PO4 structure, if you see, it's a dodecahedron, this big dodecahedron, maybe 1 micron to 2 micron size. But if you in the glass, you will get almost 4 to 5 nanometer or 6 nanometer, same size or same shape. So this is the beauty of this process. So initially, you can see it's only 600 nanometer. You can see this reflectance of this Ag3PO4. But see the absorption, the enhanced to the up to 500 to 600 nanometer. That helps a lot for the photo excitation process. So this is the hydrogen evolution you observe. This almost 1200 micromillimeter. The hydrogen evolution is taking place with this Ag3PO4 glass photocatalysis, and they are highly stable. You can see the linearity in the glass evolution is quite good. And we have done repeatedly because the beauty of this is we can repeatedly use this catalyst many times, and their generation is very very easy because just rinse with water, dry it at 100 degrees centigrade and use it. So that's why we thought that we can have the very commercial way to do this glass, and we did it. This is a big 5 kg type of block we did for silicate glasses, 4 kg, and this repeatedly we got the good results. You can see here similar type of the crystal growth inside the glass we observe, and similar type of band gap or band gap extension here we observe in these glasses. If you heated the glass very long time, then instead of quantum dots, you get the nanowires even in the glass. That is the very first time you observe. We have a 72 hours crystal heat treatment of the glass, then we can see there is a clear-cut nanowires in the glasses. And this also gives a good photocatalytic activity. 7,000 micromole per hour. It's a very good photocatalytic activity observed, and it's very stable. Then we also use this germinated glass and series, which previously I showed you. So here 7,600 is a very small amount of series, maybe 0.5%, and we are using 1 gram of glass. In that 1 gram of glass, 0.5% is almost 0.075 grams of cadmium sulfide inside the glass. Only the density of the quantum dots is much higher in the glass. So suppose you can take 1 micron glass or 2 micron glass particle, you can see 1,000 of quantum dots on the surface, and that really helps to interact with water and produce hydrogen. Here also you find that when the quantum dots is much smaller, there we get good hydrogen evolution. The enhancement rate is much enhancement as compared to bigger reactor, bigger side. Here you can clearly see this 4 nanometer has 7,560, and even to 14 it is 6,560. So it matters that when the quantum dot size is much less, then we can get high hydrogen evolution. And repeatability of this we are getting the same, because when the recovery of the catalyst is very important. Suppose you have quantum dots in the powder, recovery of this quantum dot powder is very less. But here, as soon as when it is a glass, the glass immediately gets settled. We don't need any filtration or something like that. We can just take it out and wash it with water and use it again. So that is that's why we could perform almost to the 10 times or 15 times reactions using this catalyst. Then same this silicate glass, you see why this the instead of cadmium sulfide, cadmium selenide has much hydrogen evolution, because the size of the particle is much lesser, as well as the band gap of the series is much lower as compared to series. So that also really helps to enhance the photocatalytic reaction, because more charge carriers are produced, and that really helps in getting more hydrogen evolutions. And bismuth, because bismuth has given the very huge hydrogen evolution, almost 11,541. Here also at smaller particle quantum dot size, almost 5 nanometer to 6 nanometer, gave the good hydrogen evolution, and there you can see they are highly dispersed in the glass, and because of this band gap is 1.7 electron, means their absorption is up to 800 to 900 nanometer. The whole spectrum of sunlight has been absorbed, and there are more charge carriers might have involved in this, and we get good hydrogen evolution. So this is the bigger reactor. It was giving 2 liters per hour hydrogen using normal under photochemical reactions, and I think whether we can run this. This is a video. We can see that you can clearly see the this is the photoreactor. We have the top of our roof of our laboratory. You can see that bubbles. Their intensity is much higher. These experiments have been done from 11 a.m. to up to 4 p.m. So within that the sunlight is in a good intensity, so we thought that we can use that. So this we are going to have the bigger reactor system with MIT-WPU. They have good engineering support. So we are taking that. We are also collaborating with the BSI. The same with whether we can have sugarcane juice or sugarcane waste, similar manner, as well as spent wash degradation. Spent wash degradation we have already done with Dr. Konde, and we found very good results for the spent wash degradation. This is another systems we are trying to have for more to enhance the absorption of sunlight. This work is going on. Then this another another BBSRC is a good very stable catalyst we are going to have. Then terbium doped CDS, because there is a terbium on the CDS quantum dot, and that you can see you can have the absorption in the visible region. So that work is also going on, and this is the another applications we found that this glass also can be used as an electrolyte. So this the capacity of the battery also we have shown. And work in progress is hydrogen from sugarcane juice and banana. We are trying the hydrogen production seawater. One of the group working on seawater, whether we can split seawater. We are focusing more on photocatalytic process as compared to other processes. Hydrogen process from wastewater, hydrogen from steam using iron ore. That is one of the area we have selected, because iron ore is much more iron ore is there, and where we can with catalytic process we can produce hydrogen, and again iron oxide can be reduced to iron and utilized again. So this process, the efficiency of hydrogen production is much higher. So we are trying with our MTech students. So this is my conclusion that yes, nanostructuring really helps in the photocatalytic process, and because of the nano size effect, so we can, if you can have 1 nanometer size scale in the glass, definitely it will really help to enhance in the hydrogen utilization. So this is our students like Santosh Patil and Sanjay Apte, Rajendra Panman. They have worked and different mode, and also I should thank to our collaborators because lot many other things we are doing with them, and again we are also collaborating with the SPE for the future. Thank you.